Namaste, this is Professor S. Lal from Jyoti Vidyapeeth Women's University, Jaipur, Rajasthan. Today, I am here to discuss about one of the very important aspect of optimization technique of B.TECH 6th semester in computer science and engineering stream. So learner, please you pay your attention on the syllabi of optimization technique. In optimization technique, in case of single variable function, if you are planning to stimulate something, if you are planning to get any convergent result of any problem related to your industry, your organization, then there comes into force some methods, some rules, and they are the guiding factor for you to conclude the investigation, to conclude the analysis. In nutshell, I am going to discuss here Newton's Raphson's method. So learners, you can ask that what is Newton-Raphson's method? First, here there are two names, one is Newton, another is Raphson's. Jointly they have given a method that in which circumstance we can decide the concave or convex result of a function, or the minimum or the maximum or local minimum or global maximum value of a function. So for that I am here with some study material, and I would like to share a PPT for your convenience. So just enjoy this. This is Newton's Raphson's method. I hope this is visible. And you see, Newton's Raphson methods means Newton-Raphson's scheme requires that function f be twice differentiable. Means if you are trying to apply Newton's Raphson method on a function, then the function should have some ability so that it can tolerate twice differentiation. Means if you are differentiating first, it is giving some value. If you are differentiating again, it is again giving some value in the form of variable. Then that function is applicable where you can apply Newton's Raphson's method. But in case after first differentiation, there is no variable. So there is no question of second order derivative or second order differentiation. So in that case, we can't proceed and we can't apply Newton's Raphson's method. So I hope, first of all, since you are a student of engineering, so you should keep in your mind that only those functions are applicable here where twice differentiable is possible. And the initial estimates or approximation to the stationary point or root of the equation, first order derivative means f dash x is equal to 0. So you see here f dash x is equal to 0, and means the differentiation of the function is equal to 0, and just by solving this you can get the critical values or the critical solution of this or a stationary point of this function. So a linear approximation of the function f dash x at the point x1 is constructed, and the point at which the linear approximation vanishes is taken. And as the next approximation, formally we have given the point xk, and k is any arbitrary constant and you can choose the value of k as according to your choice, x1, x2, x3, x4, like xn and xk. So to be the current approximation of the stationary point, the linear approximation of the function f dash x at xk is given by, this is the beauty, this is the actual work of Newton-Raphson's, and this function, you should remember, f dash x comma xk is equal to the differentiation of this function at the point xk. First order differentiation of this function at xk means you have taken the point xk, and the second order derivative of the function xk, the same is here, but this is second order derivative, and x minus xk, the interval of these two variables, x minus xk. We are considering this as equation 1, and we are trying to equate this to get the next approximation. So if you are putting in LHS of this equation here as equal to 0, and you are multiplying this x minus xk by this f double dash xk, then you can find the value of this xk plus 1 like this for the next approximation. And you see, to identify the region over which the following function is convex and where it is convex means whether it is, decreasing and whether it is increasing, whether it has minimum value or whether it has maximum value. So for that we are taking an exponential function fx is equal to e to the power x to the power minus 2, and illustrating the general step of Newton-Raphson's method. Here it is important to note for you that unfortunately, depending on the starting point and nature of the function, it is quite possible for Newton's method to diverge rather than converge to the stationary point. I hope this is clear. And to make your this Newton's Raphson's method very, very illustrative, understanding, and practical, I am giving an example of a numerical problem that is going to be solved with the help of Newton's Raphson's method. So you consider a function fx is equal to 2x square plus 16 upon x. Here fx is equal to 2x plus 16 upon x, and you have to minimize this function by using Newton's Raphson's method. So as according to Newton's Raphson's method, you have to take a stationary point, that is suppose x1 is equal to k, and here fx is equal to 2x square plus 16 upon x, see the cursor, and we are differentiating this, then x square will give 2x, and 2x into 2 it means 4x, and this will 16 upon x will give this 16 upon minus, I hope this will be x square. 1 minute, this will be x square. So please correct this instead of the writing. F double dash x means second derivative will be, this will be 4 plus 32 upon x cube, it is clear. And in a step 1, what you have to do, we are taking the initial value here, x1 is equal to 1. We are taking x1 is equal to 1. So f dash x1 is what? Here is f dash. Here you put x1. So x1 will be what? 4x1 plus 60 upon x1 square, and by putting x1 is equal to 1, you can find its value, but it will be minus x1. If you are putting x1 is equal to 1, here if you are putting x1 is equal to 1, then this will be giving you minus 12. If you are putting x1 is equal to 1 in this second order derivative, then it will giving you 36. So now x1 is clear. So for x2, we have already xk value. In the beginning of the slide, you have seen that in equation 1, there is a result that is giving you how to find xk plus 1. So if you are increasing by 1, so you are getting this result. Again, in step 2, this is x2. This is x2. and consequently we can find x3, x4, x5 up to the desired states, and we continue until the modulus value of the function is coming less than epsilon. And epsilon is a very lowest quantity, that is less than 0, but that is always positive. So I hope this is the practical aspect of Newton's Raphson's method. So I hope scholars, I hope students, you have got this, and by going through the concept of this, you should try to solve some numerical problems based on Newton-Raphson's method. And if you are solving one or two numerical that is based on Newton-Raphson's method, and just by using the methodology that I have adopted, with a case like a numerical problem in this presentation, it can help you more. Thank you very much. Thanks a lot.